Stand up straight for a moment. Hold your hand out in front of you, palm facing upward. Look at it. The lines crossing your palm, the tiny ridges of your fingerprints, the small hairs along the back of your knuckles. You know roughly how big your hand is. You have carried it around your entire life. In terms of the things you have direct, reliable, physical experience of, chairs and cars and houses and hills, your hand is a perfectly reasonable unit of measurement. It sits comfortably in the middle of the scale of things you understand. Now hold that thought. If you were to shrink steadily, smoothly, continuously, passing through the scale of a grain of sand, then a human cell, then a bacterium, then a molecule, then an atom, then the nucleus at its center, you would travel through roughly 15 orders of magnitude before you hit the smallest scales that current physics can describe. 15 powers of 10. Each power of 10 is not a step, but a multiplication. You are not walking down a road. You are falling down a cliff that is so deep that every time you think you have reached the bottom, you look down and find there is 10 times as much again. And now go the other way. Start from your hand and scale upward. A house, a city, a country, the earth, the distance to the moon, to the sun, to the nearest star, to the center of the galaxy, to the nearest galaxy, to the edge of the observable universe. That journey, from your hand to the furthest thing we can see, covers roughly 26 powers of 10. 26 times you must multiply by 10 to get from here to there. The observable universe is not large in the way that a mountain is large, or even in the way that the Pacific Ocean is large. It is large in a way that belongs to a completely different category of meaning. And here is the thing that should genuinely disturb you. The observable universe is not the universe. It is merely the part we can see. The part from which light has had time, in 13.8 billion years, to reach us. Beyond it, stretching outward in every direction, potentially without limit, is more universe. How much more, we do not know. It may be finite, it may be infinite, it may be so large that the word large loses all meaning in the attempt to apply it. We are going to go on a journey today through the true size of reality, from the smallest things that physics can describe to the largest structures in the observable universe, and then beyond, into the territory where the numbers stop making human sense and the universe reveals itself, scale by scale, to be something far more extreme than any intuition you have ever had prepared you for. By the end of this, if it has worked as it should, you will feel briefly and productively disoriented. You will look at your hand differently. You will step outside and look at the sky differently. You will have a clearer picture of where you actually are in the structure of things. And that picture will be, in the best possible way, deeply unsettling. The world you think you know. Let us begin at a scale you can feel. A human being is roughly 1.7 meters tall. This is what physicists and mathematicians would write as 1.7 times 10 to the power of 0 meters, or simply 1.7 meters, because 10 to the 0 is just 1. You are, at this scale, in the middle of what we might call the zone of direct experience. The things around you, a table, a tree, a car, another person, are all within 1 or 2 orders of magnitude of your own size. They are all in the range between a few centimeters and a few hundred meters. This is the scale at which your brain evolved to operate. Your senses were calibrated here, Your intuitions were built here. This is your home territory. Walk to the top of a hill on a clear day and the furthest you can see. The horizon is roughly 5 kilometers away, 5,000 meters. That is a factor of about 3,000 relative to your own height. Still within the range of direct perception, still something you can experience. The tallest mountain on Earth, Everest, rises to roughly 8,800 meters. The deepest point in the ocean, the Challenger, deep in the Mariana Trench, plunges to roughly 11,000 meters below the surface. The difference between the highest point on the solid Earth and the lowest is just under 20,000 meters, 20 kilometers. If you shrunk the Earth to the size of a billiard ball, its surface would be smoother than that billiard ball. The mountains and trenches that feel so enormous from the inside are, at the scale of the planet itself, barely a surface texture. The Earth has a radius of roughly 6,400 kilometers. This is now firmly outside the zone of direct experience. No human being has ever perceived the Earth as a whole from the outside with their own eyes, only from spacecraft, through instruments. The Earth's scale is one you know intellectually but cannot genuinely feel. You cannot stand on a hill and see the curvature of the planet. You cannot hold the Earth in your mind the way you can hold a stone. But the Earth is, as we are about to discover, one of the smaller things we will encounter on this journey. The solar neighborhood. The Moon orbits the Earth at an average distance of roughly 384,000 kilometers. That is about 60 times the Earth's radius. In 1969, it took the Apollo 11 astronauts 3 days to travel that distance. If you built a road from the Earth to the Moon and drove at motorway speeds without stopping, it would take you about 5 months. The Moon is, by cosmic standards, extraordinarily close to us. It is our nearest neighbor, the only other world a human being has ever stood on. And yet it is already at a distance that defeats direct intuition entirely. The Sun is much further. Its average distance from the Earth is approximately 150 million kilometers. A unit astronomers call 1 astronomical unit, or AU. It takes light, traveling at 300,000 kilometers per second, about 8.5 minutes to cross that distance. It would take you about 170 years to drive to the Sun at motorway speeds. The Sun itself is enormous. Its diameter is about 1.4 million kilometers, roughly 109 times the diameter of the Earth. If the Sun were hollow, you could fit more than 1 million Earths inside it. The Sun is not an unusually large star. It sits roughly in the middle of the range of stellar sizes. There are stars with diameters 1,000 times larger and stars with diameters 10 times smaller. But it is instructive, even so, to contemplate just how badly human intuition scales to the size of the nearest star. The solar system does not end at the Sun. The outermost major planet, Neptune, orbits at about 30 astronomical units, 30 times the Earth-Sun distance. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object ever built, has been traveling at roughly 17 kilometers per second for nearly half a century, and is only now approaching the edge of the Sun's magnetic influence. The solar system, in its full extent, is vast enough that even the fastest spacecraft humanity has ever launched requires decades to cross it. Beyond Neptune lies the Oort cloud. a vast spherical shell of icy bodies believed to extend anywhere from a few thousand to perhaps 100,000 astronomical units from the Sun. The Oort cloud is the source of long-period comets, bodies that spend millions of years drifting in the cold dark of deep space before a gravitational nudge sends them plunging inward toward the Sun. We have never directly observed the Oort cloud. Its existence is inferred from the behavior of comets. It is the outermost structure of the solar system, and it reaches roughly a quarter of the way to the nearest star. That nearest star, Proxima Centauri, a dim red dwarf, is approximately 4.2 light-years away. 1 light-year is the distance light travels in a year, roughly 9.5 trillion kilometers. The distance to Proxima Centauri is about 40 trillion kilometers. Voyager 1, if it were aimed at Proxima Centauri, would take roughly 75,000 years to get there. We have not left our cosmic neighborhood. We have not even properly entered it. And already the distances are so large that human intuition has long since given up. The galaxy. The Milky Way is a barred spiral galaxy. It is not a cloud or a smear or a vague collection of stars. It is a vast, structured object, a flattened disk of stars, gas and dust, roughly 100,000 light-years across and several thousand light-years thick, with a central bar of stars and 2 dominant spiral arms sweeping outward from that bar like the arms of a cosmic pinwheel. Our solar system sits in one of the minor spiral arms, the Orion arm, at a distance of roughly 26,000 light-years from the galactic center. We are, in galactic terms, in the suburbs, not in the crowded central region with its dense stellar populations and its supermassive black hole. Not out in the thin, sparsely populated outskirts. Somewhere in the middle, orbiting the galactic center at a speed of roughly 220 kilometers per second and completing 1 full orbit every 225 to 250 million years. 1 galactic year. The last time the solar system was in this position in its orbit, dinosaurs had not yet appeared on Earth. The Milky Way contains somewhere between 200 billion and 400 billion stars. Every one of those stars is a sun. Some smaller and dimmer than ours, most of them significantly so, a handful larger and brighter. If you wanted to travel from one side of the galaxy to the other at the speed of light, it would take you 100,000 years. At the speed of Voyager 1, it would take about 2 billion years. The Milky Way is not a small thing, and yet within the larger structure of the universe, it is barely a dust mote. The nearest large galaxy to our own is the Andromeda Galaxy, officially designated M31, which lies approximately 2.5 million light-years away. 2.5 million years ago, when light now reaching us left Andromeda, our ancestors were early members of the genus Homo, chipping stone tools on the African savanna. That light has been traveling through empty space ever since, and is only now arriving at our telescopes. Andromeda is roughly twice as large as the Milky Way, containing perhaps 1 trillion stars. It is visible to the naked eye on a clear, dark night as a faint smudge in the constellation of Andromeda, the most distant object routinely visible to the human eye, without any optical aid. When you look at it, you're looking across 2.5 million light-years of space with your naked eye. And Andromeda, like the Milky Way, is moving. It is moving toward us. The two galaxies are on a collision course, their mutual gravity drawing them inexorably together. In roughly 4 to 5 billion years, they will collide and merge. A slow-motion gravitational catastrophe that will scramble both galaxies over billions of years and ultimately produce a single, large elliptical galaxy. Individual stars will almost certainly not collide with each other. The distances between stars are so vast that even in a galaxy merger, two stars physically striking each other is extraordinarily unlikely. But the structure of both galaxies, the spiral arms, the disks, the organized rotation, will be shredded and randomized by the gravitational forces involved. When this happens, the night sky will look nothing like it does today. The cosmic web zoom out further, not from a single galaxy, but from the local group, the gravitationally bound collection of galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and roughly 50 smaller satellite galaxies. The local group spans roughly 10 million light-years. Zoom out further still, and the local group reveals itself to be a small cluster sitting near the outskirts of a much larger structure, the Virgo Supercluster, also known as Laniakea, a name given to it in 2014, meaning immeasurable heaven in Hawaiian. Laniakea is a gravitational superstructure containing roughly 100,000 galaxies, spanning approximately 520 million light-years. Our entire local group, with its Milky Way and its Andromeda and its dozens of satellite galaxies, is a tiny subcluster near one edge of this immense structure, and Laniakea is not the largest structure in the universe. Zoom out to the scale of hundreds of millions of light-years, and something extraordinary becomes visible. Galaxies are not scattered randomly through space. They are arranged in an intricate, filamentary structure, a vast three-dimensional web, often called the cosmic web, that is simultaneously the largest structure in the universe and one of the most beautiful. Galaxies cluster together in groups, clusters, and superclusters. These superclusters are connected by long, thin filaments of galaxies, threads of matter stretching hundreds of millions of light-years. Between the filaments are vast, almost empty regions called cosmic voids, bubbles of space that contain almost no galaxies, spanning hundreds of millions of light-years in diameter. The cosmic web looks, at the largest scales, remarkably like a three-dimensional neural network, or like the mycelial threads of a fungus, or like the bubbles in sea foam. The same branching, filamentary, node and void structure appears in all of these. A reminder that certain mathematical patterns repeat across very different systems, not because the systems are connected, but because the underlying physics of network formation is, in some deep sense, universal. The largest structures identified in the cosmic web are staggering. The Hercules Corona Borealis Great Wall, a filamentary superstructure of galaxies, spans roughly 10 billion light-years. 10 billion light-years is a distance so large that light leaving one end could not reach the other end in the current age of the universe, if the universe were not expanding. The structure is so large that it challenges our theoretical understanding of how large-scale structure can form in the time available since the Big Bang. Some cosmologists have questioned whether it is a genuine coherent structure or a statistical artifact, but similar enormous structures have been found by independent surveys. The observable universe, the sphere of space from which light has had 13.8 billion years to reach us. has a radius of roughly 46 billion light-years. Wait, you might ask. If the universe is 13.8 billion years old, how can we see things that are 46 billion light-years away? The answer is the expansion of space. The regions of the universe we are now seeing were much closer to us when they emitted the light we are now receiving. Since then, the expansion of space has carried them much further away. The most distant objects we can observe are now roughly 46 billion light-years from us, even though the light they emitted has only been traveling for 13.8 billion years. The volume of the observable universe is roughly 4 times 10 to the power of 80 cubic meters. It contains, as best we can estimate, around 2 trillion galaxies, each containing billions to trillions of stars. The total number of stars in the observable universe is somewhere around 10 to the power of 24. And this is merely the observable part. Beyond the horizon, the observable universe is bounded not by the edge of the universe itself, but by the speed of light and the age of the universe. Beyond the cosmic horizon, beyond the distance from which light has had time to reach us, there is more universe. We simply cannot see it, not because there is nothing there, but because the light from those regions has not yet had time to arrive. How much more universe is there beyond the horizon? This is a question that physics can constrain but cannot definitively answer, because the answer depends on the global geometry and topology of space. Properties that our observations, which are necessarily limited to the observable region, cannot fully determine. If the universe is spatially flat, and observations strongly suggest that it is to very high precision, then simple geometry says that the universe is either infinite or unimaginably large. A genuinely flat, infinite universe would extend without limit in every direction, filled with matter and structure arranged statistically similarly to what we see in our observable region. Inflation, the period of exponential expansion in the early universe, provides a sense of scale. Before inflation, a tiny region of space was stretched to a size vastly larger than the observable universe. The models that best fit the observed properties of the microwave background suggest that the total extent of the universe, the full post-inflationary volume, is at minimum something like 10 to the power of 23 times larger than the observable universe. That is a number so extreme it barely qualifies as a number. It means that the observable universe, with its 2 trillion galaxies and 10 to the 24 stars, is to the full universe what a single proton is to the observable universe itself. Let that sit for a moment. The observable universe, the full sphere of space containing 2 trillion galaxies, filled with the cosmic web of filaments and voids, spanning 93 billion light-years in diameter, is, relative to the full universe, approximately as significant as a single subatomic particle. And even that might be an understatement. If inflation ran long enough, and many models of inflation allow it to run much longer than the minimum, the actual universe could be exponentially larger still. In some inflationary models, the total volume of space is so large that it contains, somewhere, exact copies of every possible configuration of matter, including, yes, exact copies of you, reading this in rooms identical to this one right now. Whether this is comforting or horrifying is, as usual, a matter of personal philosophy. The quantum creation of everything In 1982, a young Russian-American physicist named Alexander Vilenkin proposed something that sounds, at first hearing, completely outrageous. He proposed that the universe tunneled into existence from nothing, not from a previous universe, not from a higher dimensional space, not from some pre-existing substrate of any kind, from genuine, absolute nothing. Vilenkin's proposal draws on a phenomenon in quantum mechanics called quantum tunneling. In classical physics, if a particle is sitting in a potential well, trapped in a valley with hills on either side, it can only escape if it has enough energy to climb over one of the hills. It cannot pass through the hill. The barrier is impenetrable. Quantum mechanics says otherwise. Because of the wave-like nature of quantum particles, there is a finite probability of finding a particle on the other side of a barrier, even if it has insufficient energy to cross it classically. The particle, in a sense, tunnels through the barrier rather than going over it. This is not a hypothetical or an approximation. It is a real and experimentally verified phenomenon. It is the principle behind nuclear fusion in the Sun. Without quantum tunneling, protons could not fuse at the temperatures in the solar core. And it is the basis of the scanning tunneling microscope. Vilenkin proposed that the same principle applies to the universe as a whole. The universe, he argued, could have quantum tunneled into existence from a state of literally nothing. No space, no time, no matter, no energy, no physical laws. Nothing whatsoever. The probability of such tunneling is not zero. It is extremely small, but in quantum mechanics, extremely small is not the same as impossible. The universe simply appeared, not from a prior cause, not from a pre-existing physical state, from nothing, through the mechanism of quantum tunneling. Before the universe, there was no before. There was no time in which nothing existed waiting to become something. The universe, with its time and its space and its matter and its energy, tunneled into existence as a complete quantum event. Vilenkin's model produces a universe that begins in a tiny, compact state and then inflates. It predicts that the universe should be geometrically flat and nearly uniform, in good agreement with observation. And it answers the question of what came before with an answer that is philosophically uncomfortable but physically precise. Nothing, not the nothing of empty space. Empty space is something, a quantum vacuum seething with virtual particles and fields. True nothing, the absence of everything, including space and time themselves. Whether this is satisfying is a matter of taste. Some physicists find it deeply compelling. The universe came from nothing because given enough quantum mechanical probability, something rather than nothing is almost inevitable. Others find it philosophically troubling. The quantum tunneling process itself requires quantum mechanical laws to operate, and those laws seem to be something rather than nothing. Where did the laws come from? Did they pre-exist the universe? Do the laws of physics exist independently of any physical reality? These questions do not have agreed answers. Downward. Everything we have discussed so far has been about going up in scale. Outward, larger. Now we reverse direction. Starting from the human scale, 1.5 meters of evolved biological machinery, we descend. The smallest thing you can see with the naked eye is typically around 50 to 100 micrometers, roughly the width of a human hair or a grain of fine sand. Micrometers, millionths of a meter. This is already a scale at which your direct experience gives out. You cannot see individual cells. You cannot feel a bacterium. Below this scale, the world becomes invisible without instruments. A typical human cell is roughly 10 micrometers across. You are made of somewhere between 30 and 40 trillion of them, each one a staggeringly complex biochemical machine running thousands of simultaneous chemical reactions, reading and copying molecular blueprints, generating energy, communicating with its neighbors, responding to signals from across the body. Each cell contains roughly 2 meters of DNA, wound and folded with extraordinary precision into a nucleus just 6 micrometers across. 2 meters of DNA in a nucleus smaller than a red blood cell. The compaction ratio is roughly 400,000. If you unraveled and joined end-to-end all the DNA and all the cells of your body, it would stretch roughly from the Earth to Pluto and back several times. A bacterium is perhaps a micrometer across, a tenth the size of a human cell. It is, compared to your cells, simple. It has no nucleus, no mitochondria, no internal membrane structure, and yet it is immeasurably more complex than any chemistry we can currently build. It contains thousands of genes, hundreds of different proteins, a complete machinery for energy production and reproduction and environmental sensing. The idea that a bacterium is primitive is a human conceit. It is not primitive. It is merely very small. Below the bacterium, we reach the molecular scale. The molecular world. A molecule of water, 2 hydrogen atoms bonded to 1 oxygen atom, is roughly 3 angstroms across. An angstrom is 10 to the minus 10 meters, 1/10,000,000th of a meter. A water molecule is small enough to fit several billion across the width of a human hair. At this scale, the universe begins to feel genuinely alien. Molecules are not the tiny smooth balls depicted in textbook diagrams. They are quantum mechanical entities. Their shapes are determined by the probability distributions of electrons. Their bonds are clouds of shared quantum probability rather than rigid rods. The chemistry that makes life possible, the folding of proteins, the copying of DNA, the generation of energy in the mitochondria. All of it occurs at this molecular scale, driven by forces and geometries that have no direct analog at the human scale. Proteins, the molecular machines of the cell, are polymers of amino acids, typically tens to thousands of amino acids long, folded into extraordinarily precise 3-dimensional shapes by the same forces that drive all molecular chemistry. Electrostatic attraction, quantum mechanical orbital overlap, the entropy-driven tendency of hydrophobic regions to hide from water. The shape of a protein determines its function. A single misfolded protein, a chain that folds into the wrong shape, can cause catastrophic disease. Prion diseases, including Creutzfeldt-Jakob disease and its cattle equivalent, are caused by a single abnormally folded protein that induces other normal proteins to misfold in a chain reaction. The difference between a functional protein and a lethal prion is a matter of 3-dimensional geometry at the scale of nanometers. The universe is, at this scale, enormously sensitive to the precise arrangement of atoms. Below molecules, we reach atoms themselves. A hydrogen atom, the simplest and most abundant atom in the universe, is roughly 1 angstrom across. Its nucleus, a single proton, is 100,000 times smaller, roughly 1 femtometer, or 10 to the minus 15 meters. The electron orbiting the nucleus is not a particle in a specific location, but a probability cloud, a wave function spread across the full angstrom-scale volume of the atom, concentrated in certain regions by the physics of quantum mechanics, but with no definite position until measured. The atom is, as Rutherford's gold foil experiment revealed more than a century ago, almost entirely empty space. The nucleus is to the atom what a fly is to a cathedral. Everything in between is the quantum probability cloud of the electrons. The hardness of matter, the reason you cannot put your hand through a table, is not caused by nuclei touching each other. It is caused by the electromagnetic repulsion between electron clouds and the quantum mechanical Pauli exclusion principle, which prevents electrons from occupying the same quantum state. Hardness is a quantum phenomenon. Solidity is a consequence of quantum mechanics. Inside the nucleus, the atomic nucleus sits at the scale of femtometers, 10 to the minus 15 meters. This is 100,000 times smaller than the atom, and it is itself not a uniform, featureless blob, but a complex, structured object. Nuclei are made of protons and neutrons, collectively called nucleons, bound together by the strong nuclear force. The strong force is the most powerful of the four fundamental forces, stronger than electromagnetism by a factor of roughly 100, but it operates only at extremely short distances. At the scale of the nucleus, it dominates entirely. At the scale of atoms, it is negligible. The structure of nuclei, the way protons and neutrons arrange themselves inside them, the quantum mechanical states they occupy, the way they respond to bombardment by other particles, is the subject of nuclear physics, a mature discipline that nonetheless still contains open questions. The nuclear shell model, the liquid drop model, the collective model, each captures some aspects of nuclear behavior and fails to capture others. The nucleus is a quantum many-body system of extraordinary complexity, and understanding it fully remains a challenge. But protons and neutrons are not themselves fundamental. Each proton is made of 3 quarks, 2 up quarks and 1 down quark. Each neutron is made of 2 down quarks and 1 up quark. Quarks are bound together by gluons, particles that carry the strong force. And here, at the scale of quarks, something deeply strange happens. Quarks cannot be isolated. Unlike electrons, which can be stripped from atoms and observed individually, quarks are permanently confined inside hadrons, particles like protons and neutrons. No experiment has ever detected a free quark. When physicists try to pull quarks apart by pouring energy into the system, the energy instead creates new quark-antiquark pairs, which immediately bind into new hadrons. The quarks remain confined. This property, called color confinement, is one of the most unusual features of the strong force, and it is imperfectly understood at a deep level. We have extremely good models of it. We can calculate its consequences with extraordinary precision using a quantum field theory called quantum chromodynamics. But the mechanism by which confinement arises from the underlying mathematics, why the theory has this property, what it tells us about the deep structure of the strong force, is an open problem that has occupied theorists for decades. The size of a quark is not well defined in the classical sense. As a quantum field theory entity, a quark is a point-like excitation of a quantum field. It has no known spatial extent, or at least any spatial structure is below our current experimental sensitivity. at scales below roughly 10 to the minus 18 meters. The Planck scale. Below the scale of quarks, we enter territory that is, at present, beyond the reach of any existing experiment. The Planck scale, named for the German physicist Max Planck, who first identified the natural units of length, time, and mass that arise from combining the fundamental constants of nature, sits at roughly 10 to the minus 35 meters. This is 10 to the minus 20 orders of magnitude below the scale of a proton. To give you a sense of how small this is, the ratio of the Planck length to the diameter of a proton is roughly the same as the ratio of the diameter of a proton to the diameter of the observable universe. Think about that. The Planck scale is to the proton what the proton is to the observable universe. The hierarchy of scales in the universe does not gradually taper off at the bottom. It plunges with the same vertiginous abandon as deep below us as the cosmos extends above. The Planck scale is where physicists expect quantum gravity to become important, where the quantum mechanical nature of space-time itself must be accounted for, where the smooth continuum of Einstein's space-time gives way to whatever granular, quantum, discrete structure lies beneath. In loop quantum gravity, the Planck length represents the minimum possible size of a quantum of space. In string theory, the Planck scale is where the string-like nature of fundamental particles would become apparent. No experiment currently in existence can probe anything close to the Planck scale, the most powerful particle accelerator ever built. The Large Hadron Collider at CERN probes scales of roughly 10 to the minus 20 meters, which is 15 orders of magnitude larger than the Planck scale. To probe the Planck scale directly with a particle accelerator, you would need a machine with a circumference comparable to the size of the Milky Way. This is not a near-future engineering challenge. It is essentially an impossibility given any conceivable technology. And yet the Planck scale is not merely theoretical speculation. It arises inevitably from combining the three most fundamental constants in physics: the speed of light, Planck's constant, and Newton's gravitational constant, into a unit of length. The universe itself, in its structure of fundamental constants, seems to be pointing at this scale as the natural boundary of the known. Below it, if below it means anything at all, lies whatever the final theory of quantum gravity will describe. Strings, or spin networks, or something we have not yet imagined. The ground floor of reality, if reality has a ground floor. We do not know. The unreasonable range. Let us now stand back and look at the full sweep of scales we have covered. From the Planck length, 10 to the minus 35 meters, to the scale of the observable universe, roughly 10 to the plus 27 meters, is a range of 62 orders of magnitude, 62 powers of 10. If you printed the Planck length as 1 millimeter on a page, the observable universe would extend for 10 to the 59 meters, a strip of paper that would wrap around the observable universe itself roughly 10 to the 32 times. The human scale sits near the middle of this range, but the middle of 62 orders of magnitude is itself a number so large it defies intuition. The universe does not gradually get bigger as you zoom out and gradually get smaller as you zoom in. It plunges in both directions with absolute indifference to human scales through layers of structure, each one of which is, taken on its own, more extreme than the last, And across this entire range, from the quantum foam at the Planck scale to the filaments of the cosmic web, the same fundamental laws apply. The same quantum mechanics that governs the behavior of quarks inside a proton also governs the chemical bonds that hold your DNA together, and the tunneling that drives nuclear fusion in the sun, and the quantum fluctuations in the early universe that seeded the formation of galaxies. The same general relativity that describes the curvature of space-time around the Earth also describes the geometry of the observable universe and the black holes at the centers of galaxies. The range of scales is extraordinary. The applicability of the laws is extraordinary. And the fact that those laws are comprehensible to beings like us, beings who evolved at a single, narrow, specific scale, is perhaps the most extraordinary thing of all. There is no obvious reason why the universe should be mathematically structured in a way that creatures the size of humans, with brains the size of human brains, operating on the time scales of human lives, can understand. The laws of nature did not have to be discoverable by us. They did not have to be expressible in mathematics that we can do. They did not have to be organized in such a way that a sufficiently careful and persistent inquiry reveals their structure. And yet here we are, discovering them. What we do not know, for all the dizzying range of scales we have mapped, there are profound gaps in our knowledge that deserve honesty. We do not know the true size of the universe. The observable universe is well characterized. Its radius, its contents, its large-scale structure are known with remarkable precision. But the full extent of the universe beyond the observable horizon is unknown and, in the most fundamental sense, unknowable with current physics. It may be finite, it may be infinite, it may be a specific finite size determined by the topology of space. If the universe has the topology of a torus, for instance, it would be finite but without an edge, and sufficiently large that the topology would leave observable imprints in the cosmic microwave background. Searches for such imprints have so far found no convincing evidence. We do not know what the very smallest scales look like. The Planck scale is the natural boundary of our current theoretical framework, but we have no experimental access to it. The correct theory of quantum gravity, which would describe the structure of space-time at and below the Planck scale, does not yet exist. The true ground floor of reality, if there is one, is unknown. We do not know whether the cosmic web, the filaments and voids of large-scale structure, has a largest scale, or whether the hierarchy of structure continues indefinitely. The discovery of progressively larger structures, from galaxy clusters to superclusters to the Great Walls, has repeatedly surprised astronomers. Whether the cosmic web has a characteristic scale at which structure stops growing, or whether ever larger structures will continue to be found as surveys improve, is an open, observational question. We do not fully understand the origin of the cosmic web. We understand broadly how small fluctuations in the early universe grew under gravity into the filamentary structures we see today. But the details of this process, particularly the role of dark matter, whose distribution shaped the web, and dark energy, whose influence on the expansion of space affected the web's evolution, contain genuine uncertainties that ongoing surveys are working to resolve. And perhaps most fundamentally, we do not know whether the scale hierarchy ends. In both directions, downward toward the smallest and upward toward the largest, we hit boundaries that reflect the limits of our current knowledge rather than the limits of what exists. Whether reality itself has a smallest scale and a largest scale, or whether the tower of structures extends without limit in both directions, is a question that the universe has not yet fully answered. Where you are, stand up again, hold your hand out, look at it. You know more now than you did when we began. You know that the hand in front of you is made of cells, each one a complex biochemical city, that those cells are made of molecules, the shapes of which are determined by quantum mechanics, that those molecules are made of atoms, each one almost entirely empty space, its nucleus 100,000 times smaller than the atom that contains it. That those nuclei are made of protons and neutrons, themselves made of quarks, themselves being point-like excitations of quantum fields. That below the quarks, physics reaches the edge of what it currently knows. You know that above you, above the roof, above the atmosphere, above the thin shell of air clinging to this rock, space stretches outward in every direction without any obvious end. That the nearest star is 40 trillion kilometers away. That the Milky Way contains several 100 billion stars and is itself just one among 2 trillion galaxies in the observable universe. That the observable universe is, relative to the full extent of space, possibly as significant as a single proton relative to the observable universe. You are a collection of quantum fields, briefly organized by evolution into a pattern complex enough to be aware of its own existence, sitting on the surface of a rock, orbiting a middle-aged star in the outer suburbs of a barred spiral galaxy, in a cluster of galaxies on the edge of a supercluster, embedded in a filament of the cosmic web. Somewhere in an observable universe of 2 trillion galaxies that is itself a tiny, possibly negligible fraction of a larger reality whose full extent we cannot see. This is not a description designed to make you feel small. It is a description designed to make you feel precisely what you are, which is something far more specific, far more precisely located, far more astonishing than small captures. You are, as far as we know, the only kind of object in the universe that can be aware of the universe's size. Quarks are not aware of anything. Stars are not aware of anything. The cosmic web, for all its enormous scale, does not know that it exists. The universe's 62 orders of magnitude of structure, from the quantum foam to the cosmic filaments, are, as far as we can tell, entirely indifferent to their own existence. Except here, except in you and in the other brief, improbable, quantum mechanical arrangements of matter that we call people, sitting on their pale blue dots, holding their hands in front of their faces, and trying, with the faint, flickering, extraordinary tools of mathematics and observation and human thought, to understand what they are and where they are and how large the thing is that contains them. The true size of reality is not, in the end, a number. It is not 62 orders of magnitude, or 2 trillion galaxies, or 10 to the power of 24 stars. The true size of reality is whatever it takes to make you feel, for even a moment, the full weight of where you actually are. Look at your hand, then look up. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.